Thank you very much. So let's hope that I can keep you interested for the last 30 minutes for today, and then we're going to start for conference dinner. So as said, oh, there are 2 more. Okay. Stay motivated. 30 more minutes. Okay. I will talk a little bit about Schrödinger operators with data potentials on unbounded Lipschitz surfaces. In particular, it will be 2 parts. First thing will be kind of some general theory about it, how to define the operator, some general results about the central spectrum, ground state, and so on. Just a little thing, how far can you push things? In particular, okay, unbounded Lipschitz graphs, but in particular, how bad may the potential be and so on. So how far can you push things for somebody who's interested in this topic? And the second part will be some application, which will be some joint work with Lipschitz from Resch and Jussi Bernd from my PhD supervisor from Graz. Some minimization problem of this lowest eigenvalue of this this Schrödinger operator with delta potential. Okay, let me start by the first thing where I introduce this operator. So formally, we consider just, this is simply the formal Schrödinger equation minus Laplace minus second derivative. And then I consider formally some potential, which is located on some curve. This is now in, let's say, arbitrary dimension for now. I will come in a minute which assumptions we have to take, and some interaction strength alpha here, which is non-constant, but some functions on this curve. So what do we consider? Surface, of course. So it's in any dimension, so okay. Yeah, so it is a surface in, it's the minus 1 dimensional surface in RD. So the way how to make this formal operator rigorous is via the quadratic form. So minus Laplace becomes more or less the energy norm, and integral over alpha, the Dirichlet trace, it takes care of this delta potential. That's the regular normal form you are more or less used to if you work in this topic. But the thing is, what do we need to assume to make everything work here? So the domain should be H1 as usual. Okay. For the surface, let's say for simplicity, I take a Lipschitz hypergraph here. So just some Lipschitz continuous function psi here, and we take just this hypergraph. And for the potential alpha, this is more what I want to talk closer to, is kind of this general. Okay, first of all, it is real valued in order to make it a self-adjoint operator in the end. And the L infinity part, so it may be only bounded at infinity and have singularities which are d minus 1 when in d larger than 3, and so L1 is not enough here, but I need something slightly larger than L1, so L1 plus epsilon function in 2 dimensions. So and this is understood, of course, alpha is the sum of a LD minus 1 function plus some bounded function on the surface. So if I assume this, I can show that this form R alpha is semi-bounded, closed, and well-defined. Well-defined in the sense that this integral exists, because it's not clear if I have a too bad alpha that this is a well-defined integral. But this is the case, and what are the basic ingredients to ensure this is, okay, we need a Dirichlet trace operator of this kind, so from HS to HS minus a half, which is kind of okay for this Lipschitz hypergraphs. And then the other ingredient we need is that for these kind of alphas we have, this is more the problematic part, is that we have it as it acts as the square root of this alpha. Why the square root? Square root because I have here the square, so I can attach one square root to the first trace and the second square root to the second trace. So the square root of this potential acts continuously from h1/2 to L2. And what is basically needed there, some Sobolev embedding theorem of this kind. And here you also see why P equals 1, this L1 space is no longer possible here. 1 plus epsilon is needed, because otherwise I had here some L infinity space, and Sobolev embedding kind of gets problematic in the L infinity setting. So this works out quite fine, and the Kato representation theorem now gives us a corresponding operator in this form. So everybody should agree on this unless we when we have this operator, this closed form here. So what is so now coming a little bit to the properties of this operator. So we know that it exists, and okay, still we have this alpha here, and this is kind of a work I did in my master's thesis. So master's thesis students don't really like Lipschitz surfaces, they do hyperplanes. And I did it there for the hyperplane case. So we get this alpha, we can, using Green's identity, integration by parts and so on, introducing also here you see the Neumann trace, and you get this kind of form of the operator domain where it's, okay, it acts like minus Laplace away from this, from the surface. So F plus is the restriction to the 1/2. So I'm more kind of in this setting that I have. This, something like this. So, and F plus and F minus are only the restrictions, F plus, F minus to this half spaces in this case when I am on the hypersurface. So this notation will be, you will see this later on more often. And it's these are the usual boundary conditions for the delta case. So the Dirichlet trace is just continuous, and the Neumann trace has a jump in the order of the potential times the Dirichlet trace. And the thing, why do I restrict myself here to the hyperplane? Is this problematic Neumann trace, which is not so clear how to define it for non-smooth surfaces. For example, what we need here, so we have only F plus minus is in H1, and the Laplace is in L2. But for normally the Neumann trace should have an HS with S larger than 3/2, but this is not the case here. So this additional Laplace gives us this space here. So more or less this H1 delta is just the first line here, but this still allows us to have a Neumann trace acting into -1/2. Yeah, and this last equation here has to then to be understood in this sense. So no, it's not an L2 equation here. Just left-hand side H -1/2, and also on the right-hand side you see I have the Dirichlet trace of F is in H1/2, and this alpha is, let's say, quite bad. So also on the right-hand side you do not end up with an L2 function, because alpha is supposed to have very bad singularities in this case. But what I did then is just improve it a little bit. So if we make alpha a little bit better, a little bit better means in this case, for d large equal to 3, we have 4/3d -1 plus some epsilon, a little bit more. And in the two-dimensional case, we have L2 plus something more. Then it turns out that we get a little bit better. So the operator domain is now no longer H1 delta, but H3 ½ delta. And also this equation down here is now, so if we have the Neumann trace is now in L2, and also alpha times the Dirichlet trace is supposed to be, so it's a better alpha, so also this right-hand side here now is an L2 equation. And also we end up with some quine-type resolvent formula. Yeah, the difference between the two resolvents is kind of this form. This one is the usual quine type resolvent formula you are maybe familiar with when you work in this direction. But for this formula to hold, this alpha is still too bad, so we had to play around here a little bit with the alphas. So the formula we came up with is kind of a shifting, a decomposition of this alpha. So I have alpha to the 1/3 on this one side, and I split it up and put the other 2/3 on the other side, and the same here, the 1/3 here and the 2/3 on this side. And so the regularity of this alpha to the 2/3 becomes better, and everything matches up to be in the right spaces to make sense here. And yeah, for instance, and if you think, okay, how can I take even this alpha to the 1/3 or 2/3? So I take more or less square roots of a function which is not assumed to be positive or anything. This is just formally, you have, if I write it correctly, it would be a little bit longer because I just decompose alpha as I just carry out the sign of alpha and then decompose only the absolute value to the 1/3 and absolute value 2/3. So if it's correctly written, you have to be here the absolute value all the time, and it doesn't matter on which one. Let's, for example, the alpha to the 1/3, I just put the sign of alpha in front and also here. So then it's really correct, but it looks nicer like this. Yeah, and this was, as I said, in 2019 when I worked on this, just on the hyperplane. But if one is able to make sure that this Neumann trace is the most problematic candidate here, makes no problems. It's also possible to extend all of this just to the Lipschitz hypergraph, but it's not done in this paper. And also, as you see here, it's done for Robin Laplacian in this paper, but yeah, more or less it's the same calculations can be done for the delta potential. It's just one on the Robin Laplacian here. You just have one half space, and on the delta you take both, and then you combine both from the sides. But the calculations are more or less exactly the same. Okay, going a little further, the essential spectrum of such a general A alpha is. What you know is for this general alphas and the hypergraph, you only know that 0 infinity is part of the essential spectrum. You can simply construct a Y sequence, you can do this. But in general, you don't have equality here. You need a little bit more because you can assume alpha to have some constant part, which is not forbidden here because L infinity shows up here. And when you have constant part, you have a shift in the essential spectrum, in particular when you have a negative constant part. And then you end up, so if alpha 0 is some constant potential, you get a negative shifted essential spectrum when it's negative. It stays the same when it's positive. But what, beside of this alpha 0, you are allowed to have some decay at infinity, which does not change the essential spectrum. And decay at infinity, or being constant at infinity in this sense, means, in the very weak sense, that for every epsilon larger than 0, this set has to have a finite measure. So it's weaker than any LP regularity or anything. It's just finite measure for all these set, which is where the function is away from 0 or away from this constant alpha 0. And now then it's possible to prove in this general setting that this essential spectrum is still minus alpha 0 squared over 4, and for negative alpha 0s and 0 infinity for positive ones. So this for the essential spectrum. For the discrete eigenvalues, so from now on, and also for the second part of the talk, for the application, we assume that lambda 1 is the infimum of the spectrum. So since the essential spectrum is an open interval to the right, it's either the lowest eigenvalue, if there are eigenvalue, but this is not the case all the time. If it's not, it's just the bottom of the essential spectrum. I don't have any results if there exists eigenvalues. There are not maybe, but there are for sure more experts in the audience which know. Babel, for example, does there exist eigenvalues and so on. For now, I will just assume if there are any eigenvalues. Then you can at least prove then if there is a discrete eigenvalue of alpha, then it is always simple in the general setting, and always the corresponding eigenfunction is strictly positive on RD without sigma. So I don't claim to be the first one who ever proved this, but maybe in this general setting, so this should be surprise nobody, but yeah, maybe in this general setting it's not stated somewhere, but yeah, it should be a general known and a known fact that the lowest eigenvalue is simple and has positive eigenfunction. Okay, now, so this was all the general part. So these are general features of this self-adjoint operator for the delta potential. And now some applications we did. So this was the one in collaboration with Lotte Reitschek and Jussi Berndt. So we want to kind of, this lambda 1 you saw before, we want to minimize it. And we've done this just for the special case of the hyperplane. So we want to kind of deform our potential in a way that we make the lowest eigenvalue, if it exists, as small as possible or as negative as possible. And of course, this is not only possible, but this makes the most sense for the hyperplane because you don't have any induced bound states from the surface and so on. So we stick to the hyperplane for now. And so maybe for convenience, what we want to do is some graphics. So for example, an easy potential is here is just a characteristic, so alpha 0 minus is here, or times beta times the characteristic functions of some set omega. So omega is on the surface, and whenever this omega, I have some characteristic function, so I have some rectangle potential. And yeah, this has, let's assume that there exists some lowest eigenvalue. And how can I make it smaller? Intuitively, of course, I have to somehow merge all these rectangles to one big rectangle here in the middle. Something like this, then there's, let's say, more space for the eigenfunction, the eigenvalue becomes lower. So kind of rearranging all these function values to the middle and make it a larger square well gives me a lower eigenvalue than this splitted one. But of course, things are more complicated. I can think of any function here. I can do a similar thing, rearranging all these function values to this one. So how do I get from here to here is, we can think of, first of all, okay, the lowest, the largest, so the most negative one is, I put him in the middle. Then I have, okay, here's something here. You can just rearrange all these eigenvalues. Then from this point on, also these eigenvalues appear, and I put it kind of radially symmetric in more dimensions, so just left and right. So make it a radially decreasing function out of this. And this is called then this alpha 1 star. This is the decreasing rearrangement. You can also think of this in a different way. You can put here these potential levels and just at some function value, this size, the length of this green line here is the same as here and here. I just shift all these, sum them up and just shift them to the middle, and this is the function which occurs. This is called so this is the intuition, how this alpha 1 star or this omega star here in the first picture looks like, because the mathematical rigorous definition of this symmetric decreasing rearrangement is kind of easy for the rearrangement of sets. So a rearrangement of set is just the same, as a ball centered at the origin with the same volume. That's quite easy to understand, but the for functions, it's kind of a little bit more problematic. So first of all, we need it to be just negative, because otherwise we run into trouble in how to rearrange the values. And secondly, we have to assume this property here, which should look familiar from the first part of the talk, where we have to have proven the stability of the essential spectrum. So all these sets have to have finite measure, so that this is a necessary assumption to rearrange all our level sets. And then we can define this property here, this alpha 1 star. This is, you don't see so much in this formula here, but yeah, as I showed you in the last page, that's more or less the way how it works. You just shift all the level sets to the center. And it has, in particular, one property that it keeps the LP norm for any P. Okay, and what we've proven now is that you can do the following. So assume that alpha is, again, constant at infinity. This kind of means that it is alpha is some alpha 0 plus some alpha 1, and this alpha 1 has some decay or some vanishing at infinity like this. So then, first of all, in this case, we know the exact value of the essential spectrum I showed you before. It's just minus alpha 0 squared over 4 when alpha 0 is negative, and it starts at 0 when this alpha 0 is positive. So the essential spectrum is known, but then the lowest eigenvalue just decreases when I go from this alpha 1 to this alpha 1 star. So alpha 1 star with a minus here, so I do not rearrange the whole alpha 1 because I said before, I only can rearrange purely negative functions. So I have to take, first of all, the negative part of this alpha 1 and then rearrange it. So it becomes smaller when I just take the negative part, and it becomes even smaller when afterwards I rearrange this alpha 1. So this was the result we obtained. Was published in spring this year. And yeah, as a corollary, the first thing where we only had this characteristic function, so when I have this lambda 1 of beta times the square well potential for any omega is larger than the square well potential where I just merge together all this and make an omega star out of it. Okay, so I don't want to go too much into the proof. Maybe I'll use my last few minutes for some, maybe first a summary, and then we'll go to page 15. So alpha, this one alpha is kind of the most singular alpha you can think of in having a proper defined Schrödinger operator coming from the semi-bounded form. We proved that the operator domain and the action of the operator gets a little bit better. So it's kind of, this equation here is an L2 equation when you are in have a little bit better alpha here, so 4, 3 over d minus 1 and L2 plus something. So maybe here I can say, okay, this epsilon, maybe one can get rid of still. Maybe this is a little bit an artifact of our of a bad estimate we made. Maybe we can just get rid of this ones and this ones. So it is expected that d minus 1 times 4/3 is enough here. You don't need an epsilon also here. But yeah, we didn't manage at the time, 2019, that to make all this estimate precisely maybe. Also an open question here is what happens in between. So we just have, okay, it was L d minus 1, and then I jump to 4/3 d minus 1, and I get jump here from h1 to h3 over 2. So what happens in between? Is there a continuous dependency? I didn't look at this problem from that time, but yeah, it's an open question. What happens in between? Is there a continuous dependency? Essential spectrum is kind of known whenever this potential is constant at infinity, in this sense, whenever this set has finite measure. And then, yeah, the eigenvalue, lowest eigenvalue is always simple and has strictly positive eigenfunction. And yeah, this rearrangement I just showed you, where we can take the negative part and the symmetric decreasing rearrangement of this alpha 1, and then we are sure that we obtain the lowest possible eigenvalue in this thing. So as I said, except of this one thing where I had problems with the Neumann trace for the Lipschitz graphs, where I just for a moment restricted myself to the hyperplane, everything only relies on kind of mapping properties and Sobolev embedding theorems of the Sobolev spaces. So it's more or less likely that all the theory can be extended to some kind of unbounded Lipschitz surfaces, which are not hypergraphs. So you kind of glue them together. And there's one thing, it's a minimum smooth domains. This is one of the Stein introduced when he extended his operator. So what you do is for unbounded Lipschitz surfaces, you find the cover of this boundary, an infinite cover, and countable cover, and then you have to assume some properties. Okay, you have some epsilon neighborhood of this surface should be inside this cover. Locally, there should be at most n of these UNs inside this cover. And inside every UN, it should locally be a Lipschitz hypergraph with the Lipschitz constant, which is bounded by. So all of them, of this infinite Lipschitz constants are bounded. Then it may be possible, or maybe under some other assumptions on the boundary, to extend all of this. So we need more or less Dirichlet trace. We need Sobolev embedding on the surface, which is maybe the most problematic part of this thing. But other than these things, and also Neumann trace is not mentioned here, other than these things, there's not many ingredients which are in this theory. But so yeah, in order to expand it, it's just only a lack of literature one has at hand to have these properties of traces and Sobolev embeddings. Okay, so for this I want to thank you. And